Here's an example now that has a capacitor and builds in some one-dimensional kinematics. A capacitor is formed by charging two 5 centimeter plates. That means that the plates are 5 centimeters on each side. They're square. Two equal and opposite charges of 1 microcoulomb. So one charge is positive, one charge is negative. Let's say that this plate is positive, this plate is negative, and both of the charges are 1 microcoulomb, and the plates are separated by 1 millimeter. First thing we're asked to find is the electric field between the plates. Well, we know electric field points from positive to negative. We know that electric field magnitude is charge density divided by epsilon naught. That's the magnitude of the field between capacitor plates. Charge density is charge over area. So we've got charge over area times epsilon naught. Our charge is 1 microcoulomb, 1 times 10 to the minus 6 coulombs. Divide that by the area, which is going to be 0.05 meters squared. Also divided by epsilon naught. Gives us an electric field with a magnitude of 4.52 times 10 to the 7 newtons per coulomb. To draw it as a vector, let's put in a coordinate system. We've set up our system so that the electric field points to the right. So our electric field is 4.52 times 10 to the 7 newtons per coulomb in the x direction, or I hat. That's part A. Part B, if we release an electron from the negative plate, find its acceleration. Well, let's see how we're going to find its acceleration. We know that force equals mass times acceleration, so we'll need the force. We know that the force on the electron is the electric force. So we've got a little electron here. It's going to be repelled by that negative plate, so it's going to move to the left. And we know that the force on it is the charge of the electron times the electric field. Charge on the electron is minus E. So I've got minus 1.6 times 10 to the minus 19 coulombs times 4.52 times 10 to the 7 newtons per coulomb in the I direction. That gives us an electric force of minus 7.23 times 10 to the minus 12 newtons. So the force is to the left. Well, we're not asked for the force, we're asked for the acceleration. The acceleration is going to be the force divided by the mass. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. That gives us an acceleration of minus 7.94 times 10 to the 18 meters per second squared I hat. So it's accelerating as it moves towards that positive plate. That makes sense because there's a force on it. Okay, part B, or part C, sorry. Find its speed when it reaches the positive plate. So now we're into a one-dimensional kinematics problem. We know that Vf squared is equal to V initial squared plus 2 times A times the distance it travels in the x direction. V initial is 0 because we release it from rest, so Vf is going to be the square root of 2 times the acceleration times delta x. So it's the square root of 2 times minus 7.94 times 10 to the 8. Oops, that should be 18. 10 to the 18, I knew that was too small. 10 to the 18 meters per second squared, that's the x component of acceleration. We multiply that by the x displacement, which is 1 millimeter to the left, so negative 1 times 10 to the minus 3 meters. Put all that through the calculator, we should get 1.26 times 10 to the 8 meters per second. I would say that's getting close to relativistic, so that might be a little unrealistic. It's almost as fast as the speed of light. Part D, how long does this whole motion take? Well, let's remember that Vf equals V initial plus A times T. V initial is 0, so T is going to be Vf divided by the acceleration. The acceleration we found in step B. And that gives us a time of 4.59 times 10 to the minus 11 seconds. That is very fast. Okay, but then that makes sense. It's not going very far, and it is moving very quickly, so it doesn't take long. For a homework question now, you can repeat the problem if you release a proton at the positive plate. You wouldn't have to repeat part A. The electric field would be the same, but go through B, C, and D. In this example, we have an electron gun creating a beam of electrons. So right off the bat, we know the mass of the particles and the charge of the particles, moving with a speed of 0.1 times c. C stands for the speed of light, 3 times 10 to the 8 meters per second, through a parallel plate capacitor with field strength 50,000 newtons per coulomb. The direction of the electric field points straight down, that's given in the picture. By how much does the beam deflect as it passes through the capacitor? So as the beam goes from left to right, how much does it move in the y direction? So let's start to think about the problem. The first thing let's sort out is what is the force on the electron, because that's going to help us learn about the motion. So the force on the electron must be an electric force. Of course, there is a force due to gravity, but that's very, very tiny, so we neglect that force. So the electric force is the charge of the electron times the electric field. The charge on the electron is minus the fundamental charge. That's times the electric field. Our electric field points down. Our charge is negative, so our electric force points up. Okay, so let's make a list of all the things that were given and let's try and think about that motion. If the force on the electron is up, then the electrons are going to move up as they pass through. They're going to get shot in horizontally. They're going to feel a force upwards. So as they move horizontally, they'll speed up as they go upwards. So this is what the path is going to look like. It's going to be like projectile motion, really. It's kind of a same problem. If you throw a ball sideways, it will start to curve as it falls to the ground because there's a force that points towards the ground. This is like this, except the force is upwards instead of down. So it moves sideways, but it starts to curve upwards because of the upward force. Okay, let's get a list of all the things that we know. Let's say that our electron enters the picture near the lower plate on the left, and it comes in with an initial velocity VI. Let's say that we take our origin where the electron starts. So our initial horizontal position is 0, and our initial y position is 0. Our final x distance is going to be at the end of the plate, so at 2 centimeters, because it goes through the entire plate. So x final is 2 centimeters. 0.0200 meters. Y final, that's what we're trying to figure out. We don't know what that is. Our initial velocity in the x direction, that's 0.1 times c, which is 3 times 10 to the 7 meters per second. Our initial velocity in the y direction is 0 because it comes in horizontally. Our acceleration in the x direction is 0 because there's no force in the x direction. Our acceleration in the y direction, we don't know yet, but we can figure this out. Okay, so we're going to try and find the y distance. We know there's a force in the y direction because there's a field in the y direction. If there's a force, then there's an acceleration. If we want to find how far it travels in the y, we're going to need the acceleration. Let's go ahead and find the acceleration. So we know that the net force is mass times acceleration. So the acceleration in the y direction is the force in the y direction divided by the mass of the electron. The component of force in the y direction points up, and it has a magnitude of the fundamental charge times the electric field. That's going to be divided by the mass of the electron. So 1.6 times 10 to the minus 19 coulombs times 50,000 newtons per coulomb. divided by 9.11 times 10 to the minus 31 kilograms gives us an acceleration of 8.78 times 10 to the 15 meters per second squared. It's positive, so it points up. Okay, so we know the force. Let's get an equation written down so we can find how far it travels in the y direction. Y final equals y initial plus v initial y times the time it travels plus a half ay times t squared. So some of these things are zero. Our initial y position is zero. Our initial y velocity is zero. So if we want to solve this problem, we need to know what is t. Well, we can find our t from our x information. Let's just move on to the next slide to do that. So to find our time, let's just remember again about the motion. The electron comes in horizontally, moving to the right. It feels a force upwards, so it will continue moving right, but it will drift upwards as it speeds up. So it's in projectile motion. As it drifts upwards, it moves to the right by a distance of 2 centimeters. So let's use our x information and see if we can find time. So we'll write down our x equation. X final equals x initial plus v initial xt plus 1/2 axt squared. X initial is 0, acceleration in the x is 0, so then our time is x final divided by v initial in the x, 0.02 meters, divided by 3 times 10 to the 7 meters per second squared. Oops, meters per second, not meters per second squared. Got carried away there. That gives us a time of 6.67 times 10 to the minus 10 seconds. So it doesn't take long to get through that 2 centimeter capacitor. Okay, let's take our t and let's put it back in our y equation. So our t will come back in here. So now our y final is 1/2 times our y acceleration times our time squared. And we get a final distance of 1.95 times 10 to the minus 3 meters, or 0.195 centimeters. We were given in the initial part of the problem that the plate separation was 0.5 centimeters, so the electron does not hit the upper plate as it travels through.